A very good morning to all present here. So, after successful completion of day one of MNDCS 2025, we are now all set to begin day two. And it is a great moment of pride and honor for all of us at NIT Silchar to have with us today an exceptional scientist, an inspiring researcher, and above all, a wonderful human being, Professor Asif Khan. So, I still remember an evening back in 2028 when I was working as a postdoctoral researcher at KAIST. So I was browsing through YouTube and basically looking for some insightful technical talks. And I stumbled upon a lecture that immediately captured my attention. The clarity of thought, depth of understanding, and passion for research in that talk left a lasting impression on me. And the speaker of that brilliant talk was none other than Professor Asif Khan. And 3 years later, I had the privilege of working with him at Georgia Tech, and that experience only deepened my admiration towards him. His scientific acumen, his ability to push the boundary of knowledge, and above all, his humility and generosity in mentoring young researchers like many of me makes him truly exceptional. Professor Asif Khan is an associate professor in the School of Electrical and Computer Engineering with a courtesy appointment in the School of Material Science and Engineering at Georgia Institute of Technology. He currently holds the prestigious Onsemi Junior Professorship. His research is at the forefront of microelectronic devices, particularly in the domain of ferroelectric devices, which are addressing some of the most pressing challenges in semiconductor technology as we approach towards the limit of transistor miniaturization. So at Georgia Tech, his research group explores every aspect of ferroelectricity, from fundamental material physics and thin film growth to advanced electron microscopy and micro or nano fabrication of next generation electronic devices. His work also extends to circuit and system level innovations for artificial intelligence, machine learning, and data driven applications. Professor Khan's contribution to the field have been widely recognized. He is the recipient of several prestigious awards, including the DARPA Young Faculty Award, the NSF Career Award, the Intel Rising Star Award, and the Qualcomm Innovation Fellowship, TSMC Outstanding Student Research Award, University Gold Medalist from Bangladesh University, and the list just goes on. His prolific research includes many book chapters, over 70 peer-reviewed journal and conference publication in leading venues like Nature Electronics, Nature Materials, IEEE Transaction Electron Devices, Electron Device Letters, IEEE International Electron Meeting, and Nano Letters. So he has delivered more than 20 invited talks and tutorials at premier microelectronics and ferroelectric conferences, including ISF, IEDM, MRS, EMA, and AVS. Today, we are privileged to have him here at MNDCS 2025 as a keynote speaker. And we extend our heartfelt gratitude to Professor Asif Khan for accepting our invitation. And we look forward for his insightful talk. So let's give a big round of applause and welcome Professor Asif Khan here.
All right. All right. So thank you so much for such a generous introduction. And this is truly my great pleasure being present at MNDCS 2025 uh, to all my friends at NIT Silchar, India, and all over the world. And I truly appreciate for inviting me for this talk. So with that, I'd like to get started. So again, I'm Asif Khan from Georgia Tech, and I'll be talking about work that we have been doing in our group for last couple of years. So I got a little bit of cold, so give me a moment to clear my throat. All right. right, so I think I hope that you can all see my screen and hear me properly. So again, thank you so much. So with that, let's get started. So before I get started, I must give credit where it's due. All the work that I'll be showing here has been done over the last couple of years in my group. And they are the best of the best. And as Dr. Das has mentioned, many of the work that I'll be presenting today here was initiated by Dr. Das. And of course, our work is sponsored by many agencies in the US and internationally. So, all right, so let me move on. All right, so my talk is about memory technologies. And memories, you would be hearing a lot about memories because AI is all rage, and what really underlies all these AI applications is different kind of memory technologies. For example, we hear a lot about GPUs, but whenever you look into the GPUs, you'll also see that a big part of the GPU boards is what they call the high bandwidth memories. For example, the NVIDIA's the latest Blackwell GPUs have 8 HBM3E DRAMs over 300 gigabytes of memory and 12 layers stacked on top of each other. There are storage memories as well. And in storage, there has been amazing progress over the years. I think currently there are like 400 layers, 5 trillion transistors there in state-of-the-art storage chips, NAND chips. Beyond traditional memory and storage applications, in the embedded space as well, there has been a lot of progress that have been made. For example, I think last year, EMRAM, embedded magnetic random access memories, is replacing embedded flash applications. And on the emerging memory memory category, Micron 2 years back unveiled their Ferroelectric based non-volatile DRAM chip, which had 32 gigabits of capacity, which is 4 times larger than the largest DRAM that is available. So my talk today is about this particular technology called storage. As I have mentioned, storage has state-of-the-art NAND storage technology is around more than 300 layers now. And whenever we think about AI, the GPUs, for example, the NVIDIA GPUs, we tend to think more about SRAM or HBM type of memories. But in fact, when you think about AI, what AI is handling a lot of data. And as well as if I think about the AI model sizes, they are also trillion parameter big. So it's both big models and big data. And as such, whenever there is an AI workflow, for example, enterprise AI, we do need a lot of NAND-based storage technologies to support the data flow that goes in and out of the HBMs. So in the coming years, it's been expected that the enterprise AI will grow fourfolds by in the next couple of years. By 2030, I think enterprise AI will reach a cap of $100 billion. And if you look at the amount of storage that will be required in the AI, enterprise AI, it's a humongous amount of storage requirement. So all that means is that we need more and more storage technologies. And what underlies this storage technology? Let's ask that question. So over the last 2 decades, there has been amazing progress that has happened in the area of storage technology, which we call the vertical NAND. What vertical NAND is basically a string of transistors where the channel is vertical like this, and the gate comes through the side. Now, what happened over the last two decades is that there has been 50 times improvement in the density of bits that one can store per unit area, and that is a large number. Now, if we step back a decade ago, vertical NAND technology was born in Samsung, and they had 24 layers of NAND. And fast forward a decade, there were 230 layers. So over a decade, 1 order of magnitude increase in the number of layers that has been achieved. And this was all happened because of not only scaling the horizontally in the XY direction, but also scaling this technology in terms of logically storing more and more bit in each of these memory cells. But going forward, if I think about next 5 years, we think that the number of layers that you'll have in the NAND technology will exceed 2000, maybe in next 5 to 7 years. However, if I think about NAND scaling towards 1000 layers, there are a number of challenges. So one thing is that if we want to stack more and more of the NAND chips into the package, what happens is that the individual dies needs to have a certain amount of thickness. And if this thickness cannot be reduced, then the package height will exceed the limit that is permitted. So what it essentially means is that we have to scale the distance between individual bits or individual devices that are there in this vertical string. And this is traditionally called the Z scaling or the mole scaling, meaning that these blocks that we see over here, these are basically gate structures, and these gate structures has to be brought close to each other. However, to bring these word lines or these close together, there are fundamental device physics challenges that might be happening. For example, if we bring these word lines too close to each other, then what will happen is that whatever data that is stored in the form of electrons or holes will start leaking into the adjacent cells, and as a result, the device performance will go down, the distribution of the devices or the memory cells will broaden to an extent that it cannot be used properly. Along with making these devices come close to each other, the write voltage also needs to be scaled down significantly. And the reason is that if I have too high a voltage, and if these word lines come too close to each other, there will be significant crosstalk between devices, which again will create a VT distribution problem. So altogether, as the technology is moving forward, there are fundamental challenges that are arising. Now, 2 years back, when we were starting to think about this problem, one of our sponsors came us and asked us a specific problem. And what they asked, they basically posed a question to us, and the question was that, can you reimagine this NAND technology with a new material class such that we can overcome these anticipated challenges of NAND scaling? So the idea is that this is the typical structure of a NAND string. Now, this may look complicated, but I'll try to break it down into simpler terms. So over here, the deep purple region is the semiconductor channel over here. This blue region is typically the region that stores the bit. This is what is called the word line. Now, in general, this structure has an overall width around 100 nanometers. So, as a result, to enable scaling, this region that is available for us to store memories is of the order of 20 nanometers. Moreover, each of these transistors or memory cells should be able to store more than 1 bits. Traditionally, we shoot for 3 levels per cell, which means that within this cell, one should be able to encode 8 levels, basically 3 bits. Or if we want to go a little bit more aggressive, quad level cell or penta level cells, 4 or 5 bits per cell, which means 16 levels or 32 levels within it. So we were given a design constraints 2 years back from our industry sponsor that can you reimagine this NAND technology where you introduce a new material that has a thickness less than 19 nanometers, the right voltage traditionally for NAND technology is around 20 to 25 volts. They gave us the parameters that, okay, can we reduce the voltage to below 15 volts? And then another parameter to enable multi-bit storage memory window, whether we can reduce it below 6.5 volts. And since we work on this material class called ferroelectrics, our choice of material was ferroelectrics. So replace the traditional charge trap nitride based technology with a ferroelectric material based technology. All right, so now that I have set the problem up, let me now introduce this material class called ferroelectrics. So ferroelectric are basically insulators in general, which are of crystalline nature. And the important part of a material being ferroelectric is that the crystalline material has to have a polar structure or non-centrosymmetric structure. For example, if you look at this crystal structure over here, you'll see that the central ion is not at the center of symmetry, rather slightly off-centered. And the precondition for a material for being a ferroelectric is that by applying an electric field larger than the coercive field, one should be able to switch the direction of this off-centering. For example, in this case, the atom is slightly off-centered on the top, which gives rise to a dipole moment or polarization upward direction. And by applying an electric field larger than the coercive field, one should be able to switch the direction of polarization. And as such, what happens is that if you take a ferroelectric material and sandwich it between 2 metal layers, you will get a capacitor that will have a hysteresis in the charge and voltage characteristics. For example, in this charge voltage characteristics or polarization voltage characteristics over here, you can see that at 0 volt, the ferroelectric material or the capacitor can be in a negative charge state and a positive charge state, meaning that this structure can work as a memory that is non-volatile. And non-volatile means that if I remove the voltage, it will still remember its state. And one level up, whenever we have a dielectric material or an insulating material, we always tend to put it in contact with a semiconductor. We can combine with a semiconductor to make it into a transistor structure. And if we take a transistor and use a ferroelectric material at the gate oxide, then the direction of the polarization can modulate the current that will flow between the source and drain. And then the current between the source and drain will actually depend on the direction of the polarization. For example, in this particular case, when the polarization is pointing towards the channel over here, you will get a IDVG curve where the threshold voltage is low. On the other hand, if the polarization is pointing upwards, then you will get another IDVG curve where the threshold voltage is higher. And just like we saw in case of a ferroelectric capacitor, in a ferroelectric field effect transistor, it will again work as a non-volatile memory, because if you look at the gate voltage 0, it can remember its states, encoding it in its current voltage characteristics. All right. So with this introduction to the ferroelectric field effect transistor, let me now move on to how a ferroelectric field effect transistor operates and how it can impact the NAND technology. So here, I am showing side by side two categories of devices. One is the charge trap flash or charge trap natride based flash, which is the common technology that underlies NAND, today's NAND technology, and this is a ferroelectric field effect transistor based structure for NAND. So in case of a traditional NAND structure, when there is electrons that are stored in this charge trap nitride layer, you have a high threshold voltage, which we say the program state. On the other hand, when a positive voltage is applied to the gate terminal of a ferroelectric field effect transistor, the polarization is pointing towards the channel, and in this case, the threshold voltage will have a lower value. Just for comparison, now if you apply a negative voltage to one of the transistors that we showed, then the remaining the electrons that are stored here will get removed, and as a result, it will shift the IV curves or the threshold voltage to a lower value. And similarly, if I think about a ferroelectric field effect transistor, then the polarization, negative voltage, the polarization will switch, and then you will get a higher voltage, higher threshold voltage here. So in principle, a ferroelectric replacement of this charge trap nitride layer can give rise to the same type of memory window functionality that one expects in a charge trap nitride based flash or NAND flash technology. All right. So with that basics, let's go on and see how does a ferroelectric field effect transistor perform and whether we can get to those metrics that we mentioned earlier. All right. Now, one of the things at the outset at the get-go of our project was that there is a notion of fundamental limit of memory window. So one of the key metric that we need to achieve for ferroelectric NAND technology is what we call the memory window, the difference between the two threshold voltages for the two different direction of the polarization. And the value that we needed was above 6.5 volts, the memory window. Now, in general, in case of ferroelectric field effect transistor, there is a well-known limit of memory window, which is basically 2 times the coercive field times the thickness. In general, ferroelectric materials has a coercive field of 1 megavolt per centimeter. So to get a larger memory window, we need a larger ferroelectric thickness. But whenever we plugged in this number of 1 megavolt per centimeter, we saw that none of the existing data actually allows us to give a 6.5 volt memory window for the thickness range of 20 nanometers. So that was kind of the limit that we were working against. And our team really needed to be innovative to design the ferroelectric material or the gate stack to get to this limit over here. And this was truly the genius of Dipjyoti, who really showed that with ferroelectrics you can reach this limit over here. And that's the story I'm going to tell you in the next 5 or 6 slides. All right. So the first thing is that, remember, we had a thickness limit of 19 nanometer for this gate stack over here. So the first thing that we did was that we deposited 19 nanometer of hafnium zirconium oxide, a very well-known ferroelectric material. And this is how the memory window versus voltage characteristics look like. So you can see that as you increase the write voltage, its memory window goes up, 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 but it reaches a maximum value of 3 volts. All right. So clearly we needed 6.5 volts. We are having 3 volts. Then Dr. Das came up with this interesting idea that, all right, how about we introduce a very thin layer of alumina and sandwich it between 2 hafnium zirconium oxide layers of 9 nanometers. Still, the total thickness is 90 nanometer because you have 9 nanometer, 1 nanometer, 9 nanometer. So 9 plus 9 plus 1, 90 nanometer. Total thickness remains the same. And very surprisingly, we saw that in this red curve that as you increase the voltage, the memory window keeps on going up, and finally it reaches a value of 5.5 volts, which is almost double that we had previously got. Okay, so that was the first interesting discovery that Dr. Das made. So going forward, then we tried a bunch of different stacks, and in this process, what Dr. Das found was that as you keep on increasing the alumina thickness while keeping the other layers same, the maximum memory window keeps on going up. And finally, after trial and error of 6 months, we were able to get a memory window that is larger than 6.5 volts for a write voltage smaller than 15 volts, which was our target. And that was the first time that anyone could show that we can beat these limits within the thickness range of 19 nanometer, the voltage range of 15 volts, and achieving more than 6.5 volts of memory window. All right. So that was an interesting observation, and we published it in IEDM in 2023. And there was a lot of questions about what the mechanisms is for increase of the memory window. So I'll not go into the details, but the main idea is that we think what is happening is that at this interface, we are essentially accumulating a lot of mobile charge that gets trapped here because of the polarization of the ferroelectric material. And more importantly, our modeling was able to show that this dielectric layer, this 1 nanometer aluminum dielectric layer, works somewhat like a tunnel dielectric. But nonetheless, it really showed or suggested that in this device, we have an interaction of polarization as well as tunneling mechanism. Both of these mechanisms interact with each other to give rise to this enhanced memory window functionality. All right. So beyond that, so that was early 2024. And then Dr. Das joined NIT Silchar. But the seed that he planted kept on growing in our group. And 2 of the junior members of our team, Prasanna Ravindran and Lance Fernandez, picked up from where Dr. Das left off, and we continued this work. So in the previous case, we showed that we had 8 nanometer 80, and then we in the middle we had 3 nanometer of aluminum. So we went on and tried different types of other materials, other choices of dielectric materials, and moved their positions around. And in this slide over here, I'm showing a bunch of different structures that we tried going forward. For example, here we had silicon dioxide, alumina, or silicon, all these materials. And we systematically changed their position as well as their thickness. And what we could clearly see that depending on the thickness and the choice of the material, the memory window can change significantly, and there are significant opportunities to engineer the performance of this structure over here. For example, in this case, we saw that putting the ferroelectric material at the bottom and the dielectric material on the top actually gives rise to significant memory window enhancement over here. This was our initial kind of a structure that Dr. Dash found, and then beyond that we started moving on, and we saw that as we move to the top we get more higher memory window. All right, so we'll talk more about it, what are the implications of moving the position of this layer around in the later slides. And then we also thought about putting not only the dielectric layer in the middle, but both in the middle and the top, and as well as bottom. So we saw quite interesting behavior. And in this particular stack over here, where we had alumina in the middle and silicon dioxide at the top, we could get the maximum amount of memory window. Again, our target was around 6.5 volts, and we could go up to all the way up to 10 volts of memory window. All right. So I'm going to summarize all the work on the memory window and the design of the stack over here. So we talked about where we stood when we started this project around 2 years ago. We thought that we cannot beat this limit of the memory window given by 2 times coercive field times thickness. And by combined effort of a lot of our team members, we could see that we actually are being able to beat this limit, actually many times on that limit. All right. This is all good and great, but what's next? So far we have said is that are great stories of success, but with all successes, we always look forward and think about the impending challenges that this technology might encounter. So one of those challenges, there are 4 challenges out there for these technologies that we currently think are important, and we need to address them for adoption of this ferroelectric based nanotechnology for upcoming generations. The first one is what is known as disturb effects. Second one is retention. Third one is endurance, and fourth one is Z-scaling. And 3 of the current members in our group, Prasanna and Lance, whose work you have already seen, and Priyanka, are working on these aspects of ferroelectric nanotechnology. So I'll probably spend 7-8 more minutes explaining some of the work that we are doing in these areas, some of the recent results, and then I'll go on to conclude the talk. All right. So disturb. So disturb is a circuit level effect that impacts the performance of a technology, and it also relates to how much you can scale a technology. So without going into without having to go into the details, the basic idea is shown here in this circuit diagram, or the physical implementation diagram over here. Say, for example, you have a program cell over here. Basically, you have stored some data here and you want to read it. In case of NAND technology, all these transistors over here are connected in series. That means that to read this cell over here, all these transistors has to be turned on and has to be very conducting. Now, what happens is that to turn them on or make them conductive, a gate voltage needs to be applied on them. But this gate voltage we have to make sure as well, when we apply a gate voltage to it, to read this program cell, we do not alter the memory that has been stored in this structure, because there is also data that is stored in here. So the problem statement is that we need to make sure that this device can be turned on without the underlying data being destroyed. For example, say this is my device over here, And if there is if this is in this state over here, to turn it on or make it conductive, we may need to apply 4.5 volt or 6.5 volt or 7.5 volts on this device. But we have to also make sure that the state of the device does not get altered. So to our not so much of excitement, what we saw is that when the device is in a certain state, for example, in this low VT state, and we apply a pass voltage, which is around 4 volts, as you keep on applying these pulses, this threshold voltage keeps on shifting. And it is a large shift from minus 1.5 volts to approximately 1.5 volts. And we apply around 10 power 7 cycles of 50 this voltage for 10 power 7 times. And this was a big challenge for this device. So going forward, what Prasanna came up with is an idea of how we can mitigate this disturb effect. So basically, these orange pulses are the pass disturb pulses that are required to turn on that transistor to enable read in a neighboring cell. But he came up with the idea that after a certain number of pulses, for example, M pulses, you can apply a refresh pulse. Now, this refresh pulse is very similar to what happens in DRAM. In DRAM, every 64 milliseconds, you have to refresh that each cell. Similarly, in NAND as well, similar pulse sometimes is applied. And he then used this pulsing scheme and applied this on our devices. And with this pulsing scheme, what we could see is that if we tune the frequency of this refresh pulse, we can actually remove the disturb effect. And what he was able to show that without any mitigation scheme, the disturb can be as high as 25% or so, but with a proper mitigation scheme, this disturb can be lowered to below 5%. All right, and this was published last year in EDL. Okay, and then we also mentioned some of the interesting effects. For example, the retention. Retention means that if we have a device, the device have to remember its state for a long amount of time, 10 years. And now, in one of the earlier slides, what we showed is that when we put silicon dioxide on top, we actually get a very large memory window. Now, however, what we was able to find out was that the devices that have the dielectric layer in the middle have much better retention than the devices that have a silicon dioxide layer on top. So basically, this slide tells us that the scheme that our team devised by putting in this dielectric layer in the middle of the stack actually has great retention at par with what we need for the NAND technology, although it is depending on the interfacial interface traps and polarization, the interaction of them. So this just validates that the original stack that our team envisions have good retention properties. All right, so we talked about 4 challenges. So 4 challenges. So As a concluding remark, what I'd like to say is that we think that disturb and retention are two aspects that we think we know how to address. But going forward, we think that one of the key challenge for ferroelectric for NAND applications will be understanding how to improve the write endurance. In general, in today's state-of-the-art NAND technology, the write endurance is around 10,000 cycles or less. So our benchmark is to have ferroelectric-based transistors for NAND applications to reach the limit of a write endurance of 10 power 8 cycles. The other aspect is that how scalable ferroelectrics are in the vertical stacks. Actually, this is what we are currently working on, understanding how does a ferroelectric field effect transistor behave in a vertical orientation like this, and how much we can scale the mold height. And the key challenge is actually to understand how the dynamics of polarization and the traps occur as we scale down these device dimensions. So if one of the young folks out there want to address some of the pressing challenges in this area, these would be two great topics to focus on, either by experiments or modeling. All right, so I'd like to just summarize what we have discussed. So ferroelectrics, we think, present wonderful opportunities for NAND storage technology, and write endurance and vertical scaling are two aspects that someone can pick up to do more work on that will be beneficial to the community in general. In this talk, I'm mostly focused on this NAND technology over here. However, if you look at the overall memory hierarchy, there are many categories out there. For example, SRAM, which are extremely fast but not dense. DRAM is denser than SRAMs but slower. And then NAND is over here, which is extremely dense but slow. Now, as technology is moving forward, each of these key technologies, NAND, DRAM, SRAM, are all scaling towards faster and better. Basically, all of them are trying to move to this corner over here. But at the same time, there are gaps between them. For example, there is a big gap between the NAND and DRAM in terms of access time and density, big gap between DRAM and SRAM. What I talked about today is ferroelectrics for NAND technology. But if you look at the overall landscape of ferroelectrics, ferroelectrics might be able to offer many things within this overall memory landscape. And so the reason I'm mentioning it is because we think that the field is wide open, and for all the young minds who wants to do some impactful work, change the world, ferroelectrics might be an interesting area for them to venture into. With that, I'd like to thank you all, and I'd like you all to come to Atlanta and visit us at Georgia Tech. Thank you so much.
So thank you, Professor Khan, for your wonderful talk. And today there are a lot of young students also who has joined voluntarily to attend your talk. And I'm pretty sure the way you have explained your research talk, I'm sure they have been able to understand at least the basic essence of ferroelectric NAND today. So I'd now like to open the floor for questions. For that, I'll go, firstly let us actually go to the online attendees. So there are approximately 50 attendees who has attending this talk online. So any questions if from the online attendees, so they can just unmute themselves and ask their questions.
Right. So I really miss the opportunity of meeting you all in person. So next time I look forward to visiting you all.
Yeah, we'll be really happy to host you here, Asif. Yeah. Uh, so if no questions from offline, then we'll go like online. Then we'll go to the offline audience. So
Dibjyoti sir, I have a question.
yeah,
Yeah,
please go ahead,
yeah.
Obis.
Yeah, thank you, Professor Khan, for your this insightful talk on this ferroelectric memory, particularly related to the NAND. I have a couple of questions. The first question is, when you are inserting this Al2O3 layer within the hafnium dioxide, so what is effect in terms of traps or reliability of the overall oxide?
Right. So I think that I mean that's a wonderful question, and I'm actually very glad to have this question. So first of all, I did not mention it. I did not have time to talk in detail about it. But what we think is happening is that polarization is one aspect of it, but also this polarization is inducing extra traps at the interface between the ferroelectric and the additional dielectric that we have. So, and in general, we see that alumina gives the best enhancement of memory window in this kind of a structure. We call it laminated structure. And we think that it's because alumina has a property of inducing traps within its bulk as well as at the interface. So long story short is that interface traps, we think, plays a big role in how this device operates and how it allows us to exceed the fundamental limit of ferroelectric memory window of ferroelectric field effect transistors. Now, second question about reliability is very important. And initially, we thought that these devices won't be reliable because they're basically depending on the traps. But to our surprise, as I was showing our recent work on EDL on the retention, so we see that the devices have actually pretty good, very good retention. So, so check mark on that one, that these traps do not impact the retention effect. So that's one thing. And endurance wise, what we see is that these devices, with or without this alumina layer, has the same endurance. So basically, alumina does not impact its endurance. Its endurance is low by itself, but having an alumina does not degrade endurance any further. So that's the second part of it. But that being said, we do need to understand the interface traps properties, because they are very important for understanding how much scalable these devices can be. Because if there are interface traps, they might actually try to move around laterally and get, I mean, it might be very similar to what today's charge trap flash based technologies key challenge is. So that is something that we need to look at more carefully.
Thank you, Professor, for your reply. One more question that I would like to ask from you. If you are just inserting a alumina layer, can we have a heterostructure of ferroelectric material just to increase the memory retention time?
Right. So we have ferroelectrics on the two sides and then the dielectric layer in the middle. So we have, I think, so we have also tried putting a dielectric on top, varying the position of ferroelectrics. So these are great ideas. So it's worth looking into.
Thank you, Professor. Just not a technical question, a general question. We are hearing this ferroelectric or in general the negative capacitance field effect transistor for a long time, for the last 1 or 2 decades. But what about the commercial application? When we are going to see the this memory chip based on this ferroelectric material?
Right. So that's a great question. And if I had known this, then I would be a billionaire, right? So this is, I mean, when a technology comes into production, I think only the ones who are at the industry forefront will know. But the thing is that 2 years ago, Micron reported their ferroelectric NVDAM technology, which was 32 gigabyte per chip, which is 4 times larger than the largest DRAM. So there are very good technologies that has been already demonstrated for ferroelectrics. Now the thing is that whether they will be commercially produced, that also depends a lot on applications space, meaning that there needs to be some applications that need that much of high density of memories. So for example, NAND technology was there since 1980s, I think, but it only became a commercially viable product when Apple came up with their iPod in early 2000s. Only then they needed NAND flash because magnetic hard drives were too bulky for portable electronics. So maybe there will be an application disruptor that will bring ferroelectrics to the forefront. So that's all we can say at this point.
Thank you, Professor, for your time. And I'm very thankful, not particularly for myself, from the NIT Silchar community for sparing your time from the busy schedule and giving this wonderful talk. Thank you. Thank you a lot. Thank you a lot.
Thank you so much, Dr. Kumar.
Yeah, so now let us take some offline questions. Yeah.
Good evening, sir.
Hello.
Hello. Hello, sir. Am I audible?
Yep.
So, good evening, sir. I have one question that is not very essentially related with this ferroelectric memory. Means, as we know, the ferroelectric may be used in the NCFET device as well as the memory technology also. So, my question is that, sir, when do we use the same ferroelectric FET for some low subthreshold swing device, or when it is considered for this memory devices?
That's a great question, right? So that's a very good question. So it's all depends on this concept of memory window, right? Sorry, I apologize, everyone. I got a bad cold for last couple of days, so I have been coughing. So if you look at this here, right? So in this case, for the two direction of polarization, there is a gap between these two IDVG curves. But if I just bring down this thickness of this ferroelectric, right, this memory window will start collapsing. And below a certain critical thickness, this and this will overlap with each other, and there will be some sharp turn-on characteristics. That's how you go from an NCFET regime to a ferroelectric memory regime of a transistor. So basically, if this ferroelectric layer is thin enough such that this hysteresis goes away, then it turns into a negative capacitance field effect transistor.
Okay, sir. Thank you.
Thank you, Dr. Chaudhary. So now I think Bibek, right? Yeah. So Bibek, who is a research scholar in the NIT Silchar, he is going to ask a question. Bibek, you can come here and ask it.
Good evening, sir.
Good evening.
Sir, my question is related to ferroelectric material actually.
Mhm.
I have studied that HF is also showing some ferroelectric property. So can it be used as a ferroelectric material so that so that insulator can be avoided and we can use only HF2 as a insulator and ferroelectric material?
That's a great question. So yeah, so the like pure, I mean, as far as I know, pure hafnia can also be a ferroelectric.
Yes.
I think it is the reason it's not as popular as other ferroelectric combinations is related to the fact that the annealing temperature needs to be higher. The polarization may not be as high, or it might be more defective. I think that's the current thought. But you may have more thoughts into it.
Okay, thank you, sir. Thanks, sir.
Okay, so any of the students have some questions? So because you will not get Asif Khan every day, so if you have some questions related to your career, or if anyone interested in higher studies, so anything that you want to ask him, so this is the opportunity for all of you. Okay, so any questions, any students? You want to ask something? Okay, I think we have one student who, and she wants to ask you something. Just introduce yourself and then ask.
Good morning, sir. I'm Anvisha Dwara, third year BTech student from the Department of Electronics and Communication Engineering in NIT Silchar. Sir, I'm really interested in pursuing higher studies. Like, can you please guide me? Like, what should I look into for my future studies or as a thesis topic?
Right. So that's a great great point. And yeah, so I think the first thing is that so if you have some research experience, that goes a long way towards getting into graduate applications. So I mean, you all know the graduate application process, and the way we do screen is that we look at the overall transcript, grades and stuff. But I think all of us put a lot of emphasis on what research you have done, how much experience you have, not necessarily on the topic. Like specific topic may not matter. What matters is that showing that you have spent some amount of time doing research, writing publication, reading papers, and all of these things actually come out very nicely when we read the personal statement that you would read. So, and on top of that, of course, please reach out to the professors at NIT Silchar, as well as anywhere else you may have. Um, if you have questions, we professors often do not reply to emails, but we do read every email. So we actually, even if we receive emails and we don't respond, but when we later see a person and we can recognize that, oh, this person sent an email and that email was very knowledgeable. So always reach out.
Okay, sir. Thank you.
Okay, Asif, so we will not keep you long. So
Sir,
just gesture of our gratitude. So
excuse me, sir.
okay, so online we have one. Okay, this will be the last question actually. So Nishi Mishra.
Yes, sir. Actually, I want to ask some question from the sir.
Yeah, go ahead. Go ahead.
Very good morning, sir. I am Nishi Mishra from IIT Jodhpur. So I am pursuing PhD in resistive random access memory. So I just want to ask that for after PhD, if we are going to do postdoc from any of the institute out of the India, so can we have since I have seen your profile also, so there are some non-volatile memory and other things also which you are fabricating and the work is going on. Can we have is there any scope for us also in random access memory, resistive random RM devices?
Yeah, of course. I mean, there are a lot of activities going on ReRAM kind of devices, right? So even at
Yes.
Georgia Tech, we have many faculty members who work on ReRAM devices. So it depends on the interests you may have and the opportunities that you may be able to avail of. Right?
Okay, sir. Different projects might be going on which can be helpful for us.
Right. So you can like reach out and you can have more, like you can like reach out to professors and others to see. So in our group, we mostly focus on ferroelectrics, but we are in general interested in a lot of different memory technologies. So yeah, you are right.
Okay, sir. Thank you, sir.
All right.
Thank
So
you.
thank you so much.
Yeah. So Asif, like just as a gesture of gratitude, we generally offer the keynote speakers a memento and a teacher.
Okay.
Now, since you are not here, so I'll take it on your behalf. Okay. So
Absolutely.
I just invite our organizing chair, Dr. Kavisharan, to just hand it over to me, and I will collect it on your behalf, Asif. Yeah.
Yeah. And when I visit you, I'll get it.
Yeah. Maybe you'll get the memento, but not the T-shirt.
Okay.
Yeah. So,
Thank you so much, and thank you so much for all your love.
yeah. Thank you, Asif. Yeah.
Have a good one.
I'll go get back to you. Yeah.